Okay, this lesson is for Mrs. Cucci's College Now Pre-Calculus class. This is lesson 7.4b, which is polar and rectangular equations. Okay, so we've been talking about these polar coordinates, and remember they have the form r theta when you graph them on the graph. We graphed the points last time. Today we're going to look at changing equations from one to the other. And the reason we're going to do this is some curves have a simpler equation in polar coordinates than in rectangular coordinates, and sometimes it looks really complicated in polar coordinates, but if we turn it into rectangular, it's relatively simple. So let's take a look at the first example. Let's say we had the equation x squared plus y squared equals 25. What we're going to do is remember from last time we had our definitions of x and y. We're going to substitute those in. So we said that x equals r times the cosine of theta. And it's x squared, so we're going to square that. And we said y was r times the sine of theta, so we're going to have r sine theta. We're going to square that. And that equals 25. And this is essentially how you're going to be changing these from one to the other, going from rectangular to polar. Just say what they equal, and then simplify it a little bit. So this is r squared cosine squared theta plus r squared sine squared theta is 25. We have r squared times cosine squared theta plus sine squared theta. And now we're just going to remember our trig identities. Cosine squared plus sine squared is the Pythagorean identity. That's just 1, so I'm left with r squared equals 25. Take the square root of both sides, and r equals 5. And that is actually our ending equation. So we took this, which was rectangular form, plugged in, and we got our polar form of the equation. Now notice how much simpler the polar form is. Instead of having x squared plus y squared, we only have r equals 5. Now some of you may remember that this equation right here is actually the equation of a circle. Say we had a regular graph. It's the equation of a circle. Remember, this is x squared plus y squared equals r squared. So radius is 5. So it's a circle centered at the origin with a radius of 5. Notice what we have here. R equals 5. R is the distance from the origin. R is the distance from the origin, and it's a constant, so it's a circle. There are no manipulations with our angles. Let's take a look at one more here. Let's say we had the rectangular equation 2x minus y equals 5. We want to convert this to polar. So I'm going to use my definitions. X is r cosine theta minus my y is r sine theta, and that equals 5. Okay. I'll do some quick simplification. Actually, I'm just going to pull out a GCF. I'm going to pull out that r, so I end up with r times 2 cosine theta minus sine theta equals 5. That's my final answer. We went from this rectangular equation to this polar equation. But this time we see that the rectangular version is actually a simpler version. I would much rather deal with that equation than start to do this. This really didn't benefit us any. So sometimes it's simpler, sometimes more complicated. Okay, so now let's take a look at going the other way. Now we've seen how to, so for the polars, we just took x and y and we substituted in what x equals and what y equals, and we're done with it. We're going to use a similar strategy for converting from polar to rectangular, but it's going to end up looking a little bit different. So let's take a look at the first example. Simplest example, one of the simplest examples you could possibly get. Say r equals 4 is a polar equation. And we would like to convert this to rectangular. Now remember, we just saw the other time, we know this is going to come out to some type of circle. And what we need to think of now is, remember how last time we used the triangle, and we said our hypotenuse was r, here's our x value, and here's our y value on a graph. And we said, you know, r equals sine of theta, r times the sine of theta times y is the y value, and r times the sine of theta is the x value. Using the cross multiplication rules. Here, we're thinking more along the lines of Pythagorean theorem. Remember, if the Pythagorean theorem for this triangle holds true, x squared plus y squared equals r squared. So no trig this time. We have an r. This is just a derivation. To get r, we have radical x squared plus y squared equals r. This is what we're going to be subbing in. So instead of r, we can write radical x squared plus y squared equals 4. I'm going to get rid of that radical. I square both sides. X squared plus y squared equals 16. And there we go. And if you notice, this is our equation of a circle. X squared plus y squared equals r squared. Our radius is 4. Radius is 4. Remember, polar coordinates are always based off the circles. That's why the circles are actually the simplest ones to do in polar coordinates. Let's take a look at another. Let's say we had r cosine theta equals 6. We know, now this time, because we have a cosine theta, it's actually going to make it simpler. We can remember our definitions from last time. Remember, x equals r cosine theta, and y equals r sine theta. We have r cosine theta here. We can replace that with x. X equals 6. Done. There's our rectangular equation. This is the equation of a vertical line written in polar form. And we convert it to rectangular form. Let's try one more here. Let's say we had r equals 2 cosine theta plus 3 sine theta. Well, we don't have an r cosine and r sine to sub that in. We could sub in r equals radical x squared plus y squared right here, but that still doesn't get rid of these cosine thetas for us. Remember, we want to get rid of all the trig functions to turn it into rectangular. What I can do, though, is multiply both sides by r. So I'm going to take this side and multiply by r, and I'm going to take this side and multiply by r. So here we have r times r is r squared equals, now here we're distributing, so I get 2r cosine theta plus 3r sine theta. Now the reason I wanted to multiply by that r was to get it into terms now that we can substitute into relatively easy right from the definitions that we know. Remember, x equals r cosine and y equals r times sine. Here we have an r cosine. I can replace that with x. Here we have an r sine. I can replace that with y. Coefficients obviously stay. Now r squared, remember, if r equals radical x squared plus y squared, in our definition that we saw above, square both sides and get r squared equals x squared plus y squared. So instead of r, I can write x squared plus y squared. And that's really as simple as it's going to get. I could solve it for y squared. I could, move it around, put the y's on one side, x or another, but this is as simple as it's going to get. This equation is definitely one of those that's simpler in polar form than in rectangular form. Okay, so I've talked about converting from one to the other. I want to move on to graphing polar equations. And to graph polar equations, we're going to do most of it right in our calculator. So, let's say, for instance, we wanted to graph 1 minus sine theta equals r. Okay, if we want to graph this equation, you head over to our calculator page, insert a new graph. And now remember, we can't type it right in. This is assuming we're in rectangular plot. The x and f of x is, of course, y. What we're going to do, in menu, go to graph, edit entry, and polar. Now you see you will get an equation. Let's say r of theta. It's like saying f of x, except it's in polar. R of theta. R equals something in terms of theta. What is it? In this case, we have 1 minus sine of theta. And I don't know where it went. Well, let's try it again. Go from the beginning again. We add a new graph, menu, graph, edit entry, polar. We get our r of theta equals, we type in 1 minus sine. Okay. One minus sine of theta. There we go. Graph it. And you see you get that little kind of heart-shaped thing. These kind of heart shapes and kind of bent circles are what we expect with a lot of the polar graphs. Not all of them, and we're going to see a couple examples of those in a second, but a lot of them. Notice also this, every time we go once around, it repeats. So like if the angle is bigger than 360, we just go once around for 360, and then we keep going around. You see that in the values. Let's take a look at another one here. There are a couple of shapes that we should know. One of them is that simple one we said before for circles. I'll add graph. Let's say this time we graph r equals 3. R equals 3, you see we get a circle, it's centered at the origin, and its radius is 3. Remember, we did two examples like this. One where we converted from polar to rectangular, one where we converted rectangular to polar, where we saw that the r equals a constant means we have a circle. It's just like saying when y equals 5, we have a horizontal line at 5, or if x equals 2, we have a straight vertical line at 2. It's the same thing, except in polar, a constant is a circle. The constant is the distance, not the position. Let's take a look at one more here. Another one. Come on. Let's take a look at 5 sine of theta. Five sine of theta, you see it looks like that. It's a circle, but it's been shifted up. And how many has been shifted up? You'll notice actually that 1, 2, 3, 4, 5. it's now, instead of being centered at the origin, it's centered so that the top of the edge is on the 5. Alright, let's take a look at another one here. Graph a polar equation. Let's take a look at 5 cosine theta. Five cosine theta is still a circle, but this time it's been shifted to the right. Sine shifts it vertically. Remember y equals r sine theta. So if we shift it vertically, we're shifting along the y-axis, so it makes sense that would involve a sine. And if we shift it horizontally, that's along the x-axis, x equals r cosine theta, so it makes sense that for 5 cosine theta, we've shifted now along the x-axis. Let's take a look at one more kind of, a little bit of a interesting graph here. Graph the polar equation 2 cosecant theta. Look at that, gives us a straight line. Now we haven't had too many straight line graphs for polar coordinates, but they do exist, and so we can go back over here. We can verify this result. So we get the graph r equals 2 cosecant theta. If I manipulate this around a little bit, r equals 2 over sine theta, using my identity. Now I cross multiply and get r sine theta equals 2. R sine theta is y. From my definitions, y equals 2. This is equivalent to the horizontal, the rectangular graph of y equals 2, which is a horizontal line at y equals 2. Notice this is what we got. Okay, so it's really the same thing. It's just expressed a different way. And just like in graphing lines, if you remember graphing lines, remember I had to have the equation in a certain form. Like graphing lines, you used to put in y equals mx plus b. Here we always need to get it so r equals something. So let's just take one more example here. Let's say we had r plus 1 equals 2 cosine 2 theta. Cosine 2 theta. Sorry about that. R plus 1 equals 2 cosine of 2 theta. We can't graph this right away in the graphing calculator. We first have to subtract 1 from both sides to get r equals 2 cosine of 2 theta minus 1. Remember that minus 1 is not part of the angle. Now we can go ahead and graph that. Put it on a new page. We're graphing still polar coordinate. And we have r equals 2 cosine of 2 theta minus 1, not in the angle, but just as a constant. And you see what we get here? We get kind of 3 or 4 loop-de-loops. I know you can't see them, the label's in the way there. So we get 4 different loop-de-loops. And that's just going to happen with various things. As you do various things, you can, as you do more of these practice problems in class, you'll start to see some patterns develop with that. We'll take a look at that. Okay, that's all the time we have today. We'll see you in class. Please bring any questions. I know this is a confusing topic.